This is Stat 101, Examples Class 10, Example 2. Now here we're doing an equal variances test for the difference in means. So our example here specifies for us that we need to do an equal variances test to determine if there is a difference in the average miles per gallon. So this is mean difference with equal variances. For this problem, we'll need to go straight into the formula sheet to check the formula for a mean difference with equal variances. So again, notice on our example, on our page here, we have the formula sheet. We can see when we're given equal variances, we can use a small sample test statistic for comparing two independent population means, assuming equal variances. And there's the test statistic there on the screen. Notice inside of this test statistic, we are pooling the variance to get a better estimation of the variance for the two samples together. So we pool the variances there, and this is the first calculation we're going to find. To find the pooled variance, we can now use that pooled variance and do the calculations that we need for it. So notice for the pooled variance, we need to get those two standard deviations and sample sizes. So moving on to the calculations, the pooled variance formula there on the screen from the formula sheet, we're finding the pooled variance SP squared. N1 is 21 from our first sample, so that's 21 minus 1 multiplied by the standard deviation 5 squared, plus second sample was 23. 23 minus 1 multiplied by second sample standard deviation squared, 3.6 squared. And the denominator values there, N1, so that's 21 plus 23, take away 2. Now, big calculation to do there, so we'll work out that top line. The top line comes to 785.12, and the bottom line there is 42. So check that you can get that calculation for the numerator. 20 multiplied by 5 squared plus 22 multiplied by 3.6 squared comes out at 785.12. So that division giving us 18.69 to 2 decimal places. Of course, when you're using a calculated value in a further formula, keep the accuracy of the calculation. Use Excel to do that calculation. So in order to find the standard error to use in the test statistic now, we need to take the square root of that pooled variance, square root of 18.69, kept accuracy in our Excel spreadsheet, multiplied by 1 over sample size 1, 1 over 21, plus 1 over sample size 2, 1 over 23. So again here, using Excel to make the calculation easier, 1 over 21 plus 1 over 23, do that bit first before multiplying. This gives us 1.7029 square rooted, and that test statistic, the standard error measure comes out there as 1.305. 1.305 for the standard error. Now, big calculations to do there. They're the hardest calculation you'd have to do by hand, but as with any of those calculations, you would have Excel to help. So, moving into our formula, using our formulas here on our hypothesis test outline, we're using the sample mean 1, population mean 1 is the mean for the sedan cars, mean 1, population mean for sedans, and mu2, mean 2 is the population mean for the vans. So we can determine in our hypothesis test whether there is a difference in the average miles per gallon. So if we're looking for a difference, then our null hypothesis will be that there is no difference. That's mean 1 minus mean 2 equals 0. No difference. And the alternate hypothesis here, when we're looking for a difference, mean 1 minus mean 2 is not equal to naught. And that means there is a difference. If it's not equal to naught, the alternate hypothesis makes it a two-tailed test. The alpha value that we were using, the two-tailed test, the alpha value that we were using is 0.05. So 0.05 for alpha, and degrees of freedom for this test statistic is n1 plus n2 take away 2. So n1 plus n2 take away 2, that was 21 plus 23 take away 2, 42 degrees of freedom. Now, in order to find the critical t-value for 42 degrees of freedom, we will be using Excel, because 42 is likely to be too big to be on the tables, the t-table. So remember the t critical values here. This is a two-tailed test, so we're taking our alpha value and dividing it by 2 and putting half at each end. Alpha over 2 is 0.025, putting half at each end to find the critical values of t. So we'll flick into Excel here. Remember, we're looking at 42 degrees of freedom, and Excel requires in the TINV critical value for the t-table, it requires a two-tailed probability, and this was a two-tailed test, so here we can put in 0.05, and the degrees of freedom was 42. So this returns us the critical value, which is 2.018. So we'll take that critical value back to our template here, and we'll put in those two critical values, 2.018 at the right-hand end and minus 2.018 at the left-hand end, which says to us that we should reject the null hypothesis if our calculated test statistic is bigger than 2.018 or smaller than minus 2.018. Now to find the test statistic. Again, we had this in the formula sheet. The test statistic is t, and it's the difference in the sample means, that would be x1 bar minus x2 bar, minus the population hypothesized mean difference, mean 1 minus mean 2 from the populations, divided by the standard error, which we calculated on the previous slide, pooled variance multiplied by 1 over n1 plus 1 over n2. Any formula like this you would take from the formula sheet. So we'd calculated that standard error measure on the denominator there, so we can bring that back from our previous slide. That was 1.305. And on the top line we have the two sample means, 22 for mean 1 minus 20.3 for mean 2 minus the hypothesized mean difference, which was 0 in our null hypothesis. So the calculation for the top line there gives us 1.7 divided by 1.305, meaning we have a test statistic of 1.303. So this time we have a test statistic 1.303, which is in the do not reject region. If we look at where that is compared with 0 and a critical value, we can see it's in the do not reject region. So our decision, do not reject the null hypothesis, because that test statistic 1.303 is smaller than 2.018. So a decision, do not reject, which means that our conclusion is we have insufficient evidence to suggest that there is a difference in the average miles per gallon for sedans and vans. Insufficient evidence to suggest that mean difference in average miles per gallon of the two car models from the example. And a conclusion should always be written in context to make sense of the problem that you are investigating. So finally, in our conclusion, we have insufficient evidence to suggest there is a mean difference in the average miles per gallon between the two car models, sedans and vans. And you can write that in many different ways, but they should make sense. And that's the end of example 2.